Hi everybody. Today my topics is shear force and bending moments. To calculate shear force and bending moments as well to sketch the diagram for that. Here there is a beam and it has two supports having concentrated load 250 kilonewtons, a concentrated moments 200 kilonewton meter and uniformly distributed load 30 kilonewton per meter. As we know, a beam resists loads primarily by means of internal moments and shears. That's why understanding of structural behavior means we have to understand the shearing force and bending moment that exist within a structural system. Regarding sign conventions for shear, moment and axial force, it is actually a matter of personal choice. We'll see that in our next slides about this. First, we have to determine the axial force at any sections. And it is done by algebraically summing the components in the direction parallel to the axis of the beam. This direction. Parallel to the axis of the beam of all the external loads and support reactions acting on the selected portions. Here, summation of Fx equal to 0. So, Ax equal to 0 because there is no axial force. Now, first, already we told about axial. Now, I have to compute the support reactions by applying equations of equilibrium and conditions to the free body of the entire beams. So we will compute Ra by summing moments of forces about support D. Here this anti-clockwise moment I considered positive. So if we take summation of moments at support D equal to 0, then we will find an equation like Ra multiplying minus 9. This is Ra. From here it is 9 meters and it is working clockwise. Anti-clockwise is positive, so clockwise will be negative. 30 into 6 into 0. This uniformly distributed load, this center, it is exactly on the support, so it will be 0, and 200 concentrated moments. This is also anti-clockwise, already I considered positive, and 250 multiply 6 because from this D it is 6 meter distance, so it is equal to 0. So Ra we got 188.89 kilonewton. Now for Rd we have to take all the vertical forces because already we got Ra, we need to find Rd, so we have to take summation of all vertical forces, that is why summation of Fy equal to 0. So what we got? RD vertically up, then 188.89 already we got here in previous slides, and minus of 13 to 6 this load downwards, so it is minus, and then minus 250, so we get RD equal to 241.11 kilonewton. This is the reactions of these supports. Now we have to find the shear. What is shear? Shear is defined as the algebraic summation of the forces to the left or to the right of any sections that are perpendicular to the axis of the member. So, to determine shear force equation for segment AB, of the beam, I take a section AA. Here we can see that AA section at a distance x from support A. So, left of this section, equations for AB will be V equal to this, because there is no other force here. That is why I wrote a x less than 3 meter greater than 0. Equation for segment BC. And another thing, at point A, shear increases, because regarding this I want to tell, at point A, shear increases abruptly from 0 to 188.89 kilonewton, because before it was Z, right now we got shear 188.89 kilonewton. So here a vertical line is drawn from 0 to 188.89 on the shear diagram. And a horizontal line we got from A to B. From A to B, this is a horizontal line. It means up to B, shear remains constant in these segments. That is why 188.89 will be horizontal. Now, using section BB, we can determine the equation for shear in segment BC. How we will do? This is x less than 6 meter, from here 6 meter, but greater than 3 meter. It is less than equal to, but this is greater than 3 meter. So here it will be this 188.89 minus of this 250. So we will get minus 61.11 kilonewton. Here abrupt change in the shear from this to this direction, from 188.89 kilometer at an infinitesimal distance to the left of B to right of B, due to this concentrated load, it will be 61.11. Now, from B to C, a horizontal line, this minus 61.11, a horizontal line at minus 61.11 it is drawn from B to C. Why? Because shear remains constant at this value from B to C. Now equations for shear in the right half of the beam, because already we checked left half of the beam, now we will check right half of the beam, and the equations for shear in segment ED and DC. This is the ED and DC, these two. So we have to use two sections, CC and DD. Equation for segment ED. Equations for segment ED. Equations for shear will be V equal to 30x1. This one. V equal to 30x1. Condition is this x1, I put here x1 because this side x, this is x1. It is less than 3 meter but greater than equal to 0. So within this range, equation is 30 into x1. This 30 and x1 distance. So shear will be 30 into x1. It means if it is 3, x1 3, then V equal to 90 kilonewtons. That is why here it is 90. Equation for segment DC. X1 range, this x1 range is less than equal to 6 meter but greater than 3 meter. So the equation will be this shear minus of these support reactions. So 30x1 minus 241.11, and putting the value x1, already 30x1 we got 90. So 90 minus this we got minus 151.11 kilonewton shear for this segment DC. That is what we can see it here. This is minus, this is plus. So like this. In my previous slides, here this part, it drops abruptly because due to this support reactions. Now for bending moment. Bending moment, we know it is the algebraic summation of the moments of all the forces to the left or to the right of a particular sections. For example, equation for segment AB. For equation AB, moment M equal to 188.89x is very clear. For AB, this support reaction multiplied by x. This one, x. If the range is x less than equal to 3, greater than equal to 0. So the moment is 566.67 kilonewton meter for segment AB. For equation for segment BC, it will be this 188.89x minus 250 into x minus 3. Here 250 into x minus 3. It's very clear. This 250, this one x minus 3, this distance, because this is 3. So this part. Because my range is less than 6 meter, greater than equal to 3 meter. So it is this zone. So moment we got 383.34. That's the thing we see here. And here 566, this is the thing we got here. Now we'll go for finding the equation for segment ED. What is the equation? Equation is minus 30x into x1 by 2. This is the equation for this. X less than equal to 3 meter but greater than equal to 0. So we get here minus 50, 15 x1 square equal to minus 15 into 9. So we got 135 kilonewton meter. This is nothing but taking moments. I mean, this is the force, this is the lever arm, so we get the moments. Same way, x1 less than 6 meter, greater than 3 meter. In this condition already we have this, and there will be addition 241.11 this support into x1 minus 3. This will be plus because this is anti-clockwise. So we get m equal to this equation, but we don't know the value of x1, and this is a quadratic equation, so we have to solve this quadratic equation. Basically we will get x1 equal to 3.99. How we will get it, we will see in next slides. Here, to solve quadratic equation, we have to solve the equation like this, considering moment this equation equal to 0. Then from this quadratic equation x1 equal to minus b plus minus square root of b square minus 4ac divided by 2a. Putting the all value from this quadratic equation, we get 3.99. So here what we got actually, here bending moment, explanation of this bending moment diagram. It is like it is linearly increases from 0 to this 566.67 at B. It then decreases linearly to the 383.34. Then the last as well, this one, last two equations for the right hand of the beam, we already saw that m decreases from 0 at E to to minus 135 kilonewton meter at D, this one, and it then increases to 183.34 kilonewton meter at an infinitesimal distance to the right of C. And here one important point is that at C the bending moments drops. Here bending moment drops abruptly by an amount 383.34 minus of 183.88 is 200 kilonewton. 200 kilonewton, this one, this concentrated load, it jumps down. Because this is the magnitude of the moment of the counterclockwise this couple. And this is the inflection points. And here bending moment is 0. That is why we solve these equations to find the value of the quadratic equation, this variable x1. And here one important point, it means this C prime, I just marked here C prime, it is 3.99 meter from end E. Or in other way I can say inflection points C prime, it is 8.01 because total is 12 meter, so minus of 3.99, so we get 8.01 meter from support A, this inflection point. That was our target to solve these equations, and we got it. So by hand calculations, in all slides we have seen shear diagram and moment diagram, and I checked all these value doing this structure analysis by software, and I found very close to this value, very close to this value. 61.11, here 61.49, here 151.11, here I got minus 152.07, here 90.57, here I got 90. So this shear diagram, structure analysis software by and as well by hand calculation, both are more or less very similar. In moment diagram also, I checked hand calculation and by structure analysis software this value, and also very similar. And that's all for today, and thanks for watching. Please subscribe.